Hello everyone, I'm Haruki Shindo from Okayama University. I'll talk about bias placement strategy for vertical stacked PCBs. First is introduction. Because of development of information society, power demand of data center increase. This is high voltage DC distribution system in data centers. There's DC-DC converter that step down DC 400 volt to low voltage like 10 volt. And this converter is often used LLC converters. And it is operated at high frequency for miniaturizations. And this converter has three characteristics. For realize high step-down ratios, a primary winding is connected by series, and the large current flow in secondary sides, so the secondary winding is connected parallel to distribute large current. And the last is center-tapped rectifier circuit for low conduction loss. So need transformers with high power density. So there are several factors to achieve transformers with high power densities. At high frequency, skin effect and proximity effect significantly occurs. So the first factor is to use PCB windings. If round winding is used, high frequency AC current concentrate at surface of windings due to skin effect. But PCB winding is very thin, so it can reduce current concentration like this. And the second is structure similar to interleave. And this is a cross-section of this center type transformers. A1 and B1 is secondary windings, and P1 and P2 is primary winding. And the secondary winding is arranged symmetrically relative to primary windings. And this reduces proximity effect. And the PCB winding is very thin, so large AC current, so it is difficult for large AC current to flow in PCB windings. So it is required parallel secondary windings. So I'll talk about one of the approach for transformers with high power densities. The approach is arrange PCB transformers horizontally like this. And this transformer is made by PCB windings. And the reflect structure similar to interleave. And, and it have parallel secondary windings like this. So, but this is very large footprint. So this is not realistic. So I introduce concept of transformer with high power densities. The concept is stack windings layers vertically. And this is PCB transformers, and that has four parallel secondary windings. And it is cross-section of these transformers. And 16 windings layers are stacked vertically like this. And this is the expansion diagram of these winding layers. And rectifier components such as diode and smoothing capacitors is mounted on top and bottom. So the secondary current flow in inner secondary windings flow into bias to top secondary windings and to be rectified. And this current flow is unusual. So structure similar to interleaf is not established a part of these PCB transformers. And furthermore, there is there are several problems. And the first is there's number of layers limit in a single PCBs, and it is difficult of heat dissipations and isolation of windings. So it is difficult to realize this concept on a single PCB. So we proposed vertically stacked PCB transformers, and this has a few characteristics. First is stack PCBs vertically by inserting the connection pin into vias, and two PCBs shared one rectifier circuit or miniaturizations. And this transformer is made by PCB windings, and this has four parallel secondary windings. And single PCBs include four winding layers. And this secondary current flow is unusual. But a new problem occurs. So current unbalance may occur depending on distance between winding layers. So loss may increase due to PCB connection by vias and distance between PCBs. So I'll talk about evaluation targets of losses and purpose of these studies. So there are three evaluation targets of losses. And this is the top PCB layers. And this is an enlarged view of these areas. And a secondary current from these vias and rectifier diode and smoothing capacitors. And this is opposing current. So this causes current concentrations. So we named loss ones. And this is an enlarged view of these areas. And secondary current flowing into vias generate magnetic field. And the magnetic field induce many eddy currents. So we named loss twos. And the last is current unbalance because of distance between PCBs. So the purpose of this study is evaluate three losses by experiments and electromagnetic field analysis, and extract strategies for PCB stacking. So before experiments, I'll talk about contents to be compared in the experiments. So we made 8 prototypes with different via placement and PCB spacing. And first, we produce prototype 1 to prototype 4 with different via placement and compare them to evaluate lost ones. And the second, we produce prototype 5 to prototype 8 and compare with different PCB spacing, like prototype 1 and prototype 5, to evaluate loss 2 and loss 3s. So first, we conducted experiment 1 to evaluate loss 1s. In this experiment, compare AC resistance instead of loss. And the resistance of loss 1 cannot be measured directly. So there is calculation method for AC resistance of loss 1. So R loss 1 equal R prototypes minus R concept. So the R concept is calculated resistance where loss 1 don't occurs. So this is the measurement method of R prototypes. So we conducted short tests without iron loss. LCR meter is set by primary side, and the diode and capacitors on secondary side is shorted by copper foil, and the another diode is opens. And this is a calculation method of our concept. First, we measured a single PCB transformers like this, And we defined R1 and R2 for AC resistance of primary and secondary windings. So R1 plus 36, R2 equal 251 milliohms. And this is measurement values. And we twice these values. So we can calculate R concept. So this is conversion result at 1 megahertz. Uh, to compare R prototype 1 and prototype 4, this is about 30% reduction of losses. But not fastly is R prototype 3 and R prototype 4. And this is only difference from the distance between H and vias. But this is about 10% reduction of losses. So placing vias away from the edge and distribute them minimize proximity effect. So the next slide, we analyze prototype 3 and prototype 4 to estimate the cost. So we conducted analysis once, and this is analysis models. And diode and capacitors are shorted by diode and shorted by copper foils, and the DC current path is omitted for simple analysis. And this is analysis conditions. And we set current source and that have sine waves have 1 ampere RMS and 1 megahertz. And the diode and capacitor are shielded by copper foils. And this is analysis result. And compare by current densities, prototype 3 and prototype 4. As most of the current from these pairs concentrate around H, and this is opposing directions. So prototype 3 cause current concentration significantly. And on the other hand, in prototype 4, the current flows this bias flow diagonally. So the amount of the current near the edge is less than prototype 3's. So prototype 4 reduce these current concentrations. So distributing bias away from the edge, current concentration near the edge. So we conducted experiments to evaluate loss 2 and loss 3's. And this is a comparison result. Increasing the PCB spacing in any bias placement minimize the resistance. So we conducted analysis using placement 4 as example to investigate whether eddy current or current unbalance influence the experimental result dominantly. So we conducted analysis to verify the current balance with PCB spacing change. And this is analysis models. And this is a cross-section of these transformers. A1 and A2 is a secondary winding that analysis that analysis targets. And this is a circuit diagrams. And this is a, analysis result. So from this result, increasing the PCB spacing significantly improved current balance like this. And the last, we conducted analysis trees to verify whether current balance or eddy current influence dominantly. And this is a cross-section of transformers, and A1 and A2 is a secondary windings, and that's simulation targets. So the contrast of A1 and A2 is more vivid than these models. So this reflects current balance. But the areas where eddy current occur possibility, red circuit and orange circuit, and no significant change, um, and no significant change, um, despite changing PCB spacing. So the effect of eddy current is small. So, so the effect of current balance is more than effect of eddy currents. So this is the summaries. We got two strategies for vertically stacked PCBs. And the first is distribute vias away from edge and reduce areas near the edge. And there is trade-off between PCB spacing and current balance. And the conclusion is vias placement and PCB spacing may be important design points in PCB multilayering. Thank you for your attention.